Mission systems are increasingly called upon to process classified information. Information sharing may occur based on need to know. To reduce cost, mission components may be shared across many platforms that need to operate at different security levels. These platforms may be linked to control systems that provide a common operational picture for the mission. Aspects of that common operational picture may be shared with coalition partners who are not cleared to see all of the information available on the mission system. The challenge is to build cost-efficient platforms that can share information securely while promoting high component reuse. Since multi-level secure systems have traditionally proved costly to build, many mission systems today operate at system high, but doing so makes data sharing with coalition partners much more difficult. What is needed is an effective security architecture, but what is needed even more is a way to assess that architecture early in the requirements and design phase to avoid fixing costly mistakes later. Model-based engineering, as exemplified by the Architecture Analysis and Design Language, or AADL, has been shown to be successful for assessing emergent system properties like safety, fault tolerance, and performance early in the design. Since multi-level security is also an emergent system property, our research answers the question, what is needed to apply model-based engineering to multi-level security? The Multiple Independent Levels of Security, or MILS architecture framework, has demonstrated itself to be a cost-effective approach for building multi-level secure systems. Under MILS, mission functional components are implemented as single-level systems, each of which effectively operates at system high. Multiple instances of these components running at different security levels can be combined on a single platform called the separation kernel. The separation kernel is trusted to isolate mission components operating at different security levels. To enable the cross-domain information flows required of a multi-level secure system, MILS introduces dedicated cross-domain solutions. Each cross-domain solution is tasked to enable the transfer between different security levels. MILS reduces the cost of development because both the separation kernel and cross-domain solutions were previously certified. So the main concern for the mission system certifier is confirming that the system was constructed according to MILS principles. The tool that we will describe next introduces the ability to assess mission systems modeled in the AADL against the MILS principles. To illustrate the MILS security analysis tool in action, we shall use the simple system illustrated here. This system is composed of multiple participant subsystems connected to a single ground control subsystem. Within the participant subsystems, mission sensors can operate at different security levels, while the GPS and clock operate at the same level. The ground control subsystem includes briefing room displays for both mission high briefings and coalition briefings. The problem illustrates two challenges for multi-level security. First, each subsystem is multi-level since it accepts inputs and produces outputs at different levels. Second, the composition of these subsystems is multi-level. The problem also illustrates the challenge of promoting component reuse. We would like participant subsystems to share many of the same components. Our demonstration will highlight how the MILS tool supports component reuse. The MILS Security Analysis tool for AADL is a plug-in for the Eclipse Integrated Development Environment. It provides the following features to support the developer of a MILS-based system. First, the tool introduces a new component property called the security level. To minimize the model annotation needed to support the analysis, this property is expressed only for components that interface with the system's environment, and it is expressed only in the integrated system model. To minimize the sensitivity of the model, abstract levels such as L1 and L2 can be used instead of standard military classification labels. This notional diagram illustrates the abstract security levels applied in context. Second, the tool will automatically derive the security levels for all interior components. The tool follows all model connections between components to derive these levels. During this process, the tool will detect any component that could potentially observe information at more than one security level, and it will report the violation. At this point, the developer needs to add abstract components to the model to stand in for certified cross-domain solutions that will be deployed at these locations. The cross-domain solutions effectively partition the model by security level. The developer can rerun the tool at any time on the updated model. Our first demonstration will highlight potential cross-domain flows within the participant subsystem. Here we see the participant subsystem model as displayed within the OSATE tool. This model illustrates the components of the participant subsystem, including the mission sensor, the GPS, the clock, and the communication medium. When we view the security level properties associated with this model, which are highlighted here, we can see that the participant subsystem can observe 3 security levels: L0 at the mission sensor, L1 at the GPS and clock, and L5 at the communications medium. Now we want to run our analysis across this model. Our analysis returns the first error encountered, which is that an interior component, the data link component, can observe both L1 and L5 information. To fix this error, we introduce a cross-domain solution into the participant subsystem to change the level of information to L5 from L1 before it reaches the data link component. Notionally, this cross-domain solution may perform red-black separation by encrypting red L1 data, yielding black L5 data. Once all errors in this component are addressed, we move on to analyze other components. At this point, all of the potential cross-domain information flows in the participant subsystems have been addressed, and cross-domain solutions have been added to those models where needed. Now we turn our attention to composing these participant subsystems with the ground control subsystem. Here we see the ground control subsystem model. This model illustrates the components, including the communications medium, the briefing displays, and the sensor control. When we view the security level properties associated with this model, which are highlighted here, we can see that the ground control subsystem can observe 4 security levels: L5 at the communication medium, L3 at the first briefing display, L4 at the second briefing display, and L1 at the sensor control. When we run our analysis across this model, our analysis returns multiple errors about data at L3 and L5. To fix this error, we need to introduce a cross-domain solution to decrypt L5 back to its original level. But we also need to introduce cross-domain solutions to transform the decrypted information to L3 and, as well, L4 for each of the briefing displays. This would be accomplished by guards. Here we see the resulting ground control subsystem model after the appropriate cross-domain solutions have been added. In total, 5 abstract cross-domain solutions were added to the ground control system model: 3 decryptors and 2 guards. Here we see displayed the complete set of security levels for the integrated system. The system certifier can compare the required levels assigned to each cross-domain solution against available product offerings. Eventually, we envision a library of specifications for approved cross-domain solutions that can be used to instantiate these abstract components. We run our analysis against the updated integrated model one more time. With no errors, the tool confirms that the system as modeled is successfully partitioned by security level using cross-domain solutions. By specifying the security level properties only in one place, the integrated systems model, the MILS security analysis tool for AADL minimizes the modeling burden while promoting component reuse within the AADL model. The MILS tool highlights for the system certifier exactly what cross-domain information flows are required and where they occur. For more information about the MILS security tool for AADL, please use the contact addresses listed at the beginning of this video.